Hi, it's Paul here to teach you how eigenvectors and eigenvalues were taught when I was an undergraduate, when I was in the physics department, and indeed pretty much everywhere in the world until about 1995. I'm going to set up small margins on the screen but leave a little bit of room on the left just in case I need it, and set up with axes so I can display some vectors in R2. Let's start out with the matrix A that also appears in the executive summary and try to visualize what it does to various vectors. This is tricky to do with pencil and paper, but easy to do in R. So let's try with V1, the first standard basis vector, and apply A to it to calculate W1. In the first call to arrows, I set LTY equal to 2. That gives a dotted line. Then the second call to arrows, where I plot W1, I use the default solid line, and you can see what happens. The dotted red vector gets turned into the solid red vector, different magnitude, different direction. And if you pick almost any vector in the plane, like this W2, which I've chosen arbitrarily, the same thing happens. The dotted blue vector gets rotated and stretched. But there's an exception. Look at V3. V3 is the vector 1, 1. I plot it in dotted green. I apply A to it and plot the result in solid green, and you can see what happens. That vector just got multiplied by 3. So here's some new long words for you to learn. The vector in question is called an eigenvector, and the quantity 3 by which it got multiplied is called an eigenvalue. The eigenvector is ambiguous in the sense that I could multiply it by any scalar and it would still be an eigenvector. Now it turns out there's one more exception. The vector V4. I'll explain shortly how I could have discovered these. This time I start by plotting the vector as a dotted magenta arrow, plot the effect of A on that vector as a solid magenta arrow. I overwrote the dotted one. That means I have found an eigenvector with eigenvalue 1. We've got two vectors in R2. They're not linearly dependent. They form a basis. And since they form a basis, I can write any vector in terms of them and thereby figure out very easily what happens to any other vector. Simple example. I take V3 minus V4 and call it V5. Now that I know that V3 and V4 are eigenvectors, I just have to multiply V3 by 3, multiply V4 by 1, and I have figured out the effect of A on V5, and you can see I've got two different ways of calculating the result 1, 2. Now let's get a bit tricky. It's obvious at this point that multiplying the matrix A by V3 has exactly the same effect as multiplying 3 times the identity matrix by V3. And therefore, if I take the difference, A minus 3 times the identity matrix, and multiply that by V3, I get 0. That means that the matrix A minus 3i takes V3, which is a non-zero vector, and maps it into the 0 vector. V3 is a vector in the kernel. As you now know, the dimension of the kernel plus the dimension of the image is the dimension of the domain, 2 in this case. If the kernel is one-dimensional, the image can only be one-dimensional. That means that A minus 3i cannot be surjective, cannot be onto, and it's therefore not invertible. Another way of looking at this, if I calculate its determinant, I get 0. I can do the same thing with the other eigenvector, A4. If I subtract off 1 times the identity, again, I find that the determinant of the resulting matrix is 0. As I mentioned, any vector in R2 is a linear combination of V3 and V4, and that means if I apply the product of A minus 3i and A minus I to a vector. The A minus I will hit V4, map it into 0. The A minus 3I, which could perfectly well have been applied first because those two matrices commute with one another, would map V3 into 0, and therefore the product maps everything into 0. In fact, if I take the matrix product of these two matrices, it's the 0 matrix, which maps everything into 0, and we have discovered the characteristic equation approach to finding eigenvalues. Form the matrix A minus T times I. Its determinant is the characteristic polynomial, conventionally symbolized by the Greek letter chi. So chi is a function of t, and since R will not do symbolic algebra, we have to work this out mentally. Look at the matrix A down at the bottom of the screen. To calculate its determinant, I take minus 1 minus t, multiply by 5 minus t, and then subtract off the two entries on the off diagonal, subtract minus 2 times 4. There is my characteristic polynomial. And while I can't do computer algebra in R, I can sure enough use the curve function to plot this. And the plot, combined with a horizontal red line at the value 0, makes it clear that 1 and 3 are the solutions to the characteristic equation, the eigenvalues. In the 2 by 2 case, though not more generally, it's easy to find the eigenvectors once you know the eigenvalues. Here's my reasoning. The matrix A minus 3I, we've agreed, has a one-dimensional kernel. It's spanned by the eigenvector V3. Any vector in this two-dimensional space is a linear combination of the basis eigenvectors V3 and V4, and therefore if I hit this arbitrary vector V with A minus 3I, the term involving V3 gets killed off. What's left is a multiple of V4, and we have found the other eigenvector. Similarly, on applying A minus I to this vector V, I get a multiple of V3. So, simply speaking, the image of the matrix A minus 3 times I is a multiple of the eigenvector for the other eigenvalue, 1, while A minus I applied to any vector reveals the eigenvector for eigenvalue 3. Would that everything were that simple, but there are 2 by 2 matrices that don't have real eigenvalues, and you're familiar with some of them. You know about conformal matrices. Here's a conformal matrix, and as you know, this represents the complex number 1 plus 2i. Let's work out its characteristic polynomial. Look down the main diagonal, 1 minus t times 1 minus t. Look at the off diagonal, add on 4, and plot the resulting function from -1 to 3. You can see this is a quadratic polynomial whose minimum value is 4. It never intersects the line at 0. It has no real roots. And in this case, if we ask what happens to various vectors, we can look at what happens to the first standard basis vector. As you already know, it gets rotated and stretched. The same thing happens to any other vector. There are no real eigenvectors. There are no real eigenvalues. What are the eigenvalues? Well, you know that the conformal matrix that we're considering represents the complex number 1 plus 2i. If I subtract 1 plus 2i from the conformal matrix, then I get a matrix B. It has complex entries, mind you, because I have subtracted 1 plus 2i times the identity matrix from it. R refused to calculate the determinant of this matrix. It said determinants of complex matrices were not yet implemented, but I can do it by hand, and sure enough, it comes out to be 0. So, in the case where the characteristic polynomial has complex roots, the matrix has eigenvalues, but they're complex. It has eigenvectors, but they have complex components. Most people would rather not deal with complex numbers if they can avoid it, and I'll show you in a while how to do that. But let's conclude with one other troubling case. Here's an innocent-looking matrix A. Let's work out its characteristic polynomial, going down the main diagonal 3 minus t times 5 minus t. From the off diagonal, we get plus 1. And when I plot this, I see that the parabola is tangent to the red horizontal line at the value 4. This is a quadratic polynomial with a double root. The characteristic polynomial is t minus 4 squared. That means I have found only one eigenvalue. And in this case, there is one eigenvector with eigenvalue 4. I can work it out by applying a minus 4I to the vector of my choice. And there it is. The eigenvector is 1, 1. It gets multiplied by 4. Any other vector, the direction gets changed. I picked one rather arbitrary example, but trust me, there's no way you're going to find a second eigenvalue. There is no second root to this characteristic polynomial, nor can you find a second independent eigenvector. What's going to complicate the situation is that there are cases where, although you can find only one eigenvalue for a 2 by 2 matrix, you can find two independent eigenvectors. The simplest example is the identity matrix. There the only eigenvalue is 1, but every vector is an eigenvector with eigenvalue 1. That concludes this recorded R script, and we'll move on to the modern way of doing this in the next R script.